For this example, we've got a light scale pan that's attached to a vertical light inextensible string. So this is the string here. It says the scale pan carries two masses, A and B. Mass A is 400 grams and mass B is 600 grams. So A rests on top of B as shown in the diagram. It says the pan is raised vertically using the string with acceleration 0.5 meters per second squared. It's being raised, so it's being raised upwards with an acceleration of 0.5 meters per second squared. Now we know that these weights are going in the downward direction, so the force of the weight is going down, which means that we must have tension in the string going upwards. And we know that we've got overall a weight of, so W equals mg. So the mass here, which is usually in kilograms, we've actually got it in grams. So this is 0.4 plus 0.6 g. Part A, we're asked to find the tension in the string. So I'm going to resolve vertically for the whole system. So in the vertical direction, we're using F equals ma. We've got T, subtract 0.4 plus 0.6 g. That's equal to mass times acceleration. So we've got 0.4 plus 0.6 multiplied by our acceleration, which is 0.5. So we get here T subtract G is equal to 0.5. Remember, G is equal to 9.8. So that means that T equals 0.5 plus 9.8, which is 10.3 newtons. So that's our value for T. Now it's asked for the tension in the string, so I'm going to write a statement saying the tension in the string is 10.3 newtons. For part B, we're asked to find the force exerted on mass B by mass A. So what that means is we want that normal contact force for mass A. So if we look at mass A, which is 400 grams, we've got the weight of mass A is 0.4 g newtons. We've got the normal contact force R. So the force exerted on B by mass A is that normal contact force that A has, because the normal contact force of A will be exerted onto B because A is on top of B. And we've got our acceleration is 0.5. So we're just going to resolve our forces in the vertical direction just for mass A. So for A only, we're resolving upwards and we get R subtract 0.4 g is equal to 0.4 multiplied by 0.5, F equals ma. And if we rearrange this, we get R is equal to 0.4 times 0.5, subtract 0.4 g, remember g equals 9.8, put that in your calculator and you get R equals 4.12 newtons. And again, we're going to write that closing statement. So we're going to say the force exerted on B by A, so the normal contact force of A, is 4.12 newtons and it's going downwards. Remember, force has a magnitude and direction. So its magnitude is 4.12 newtons, and we know it's going downwards. So the reason that we know it's going downwards is because the force that's exerted on A by B, we're going to use, which is that 4.12 newtons, that normal contact force. We're using Newton's third law to say that the force exerted on B by A will have the same magnitude but it's in the opposite direction. So we found out the normal contact force, the force B has on A, and then we're using that, we know that our forces are opposite and equal to say that the force going exerted on B by A must be equal and opposite. So we've got 4.12 newtons but in the opposite direction. For part C, we're asked to find the force exerted on B by the scale pan. So if we just redraw our diagram, so we've got our tension in the string here, we've got our acceleration, and we're going to find that force going downwards, so we're finding the force exerted on B by the scale pan, so that force going downwards. So if we resolve upwards, now we are told in the question that the scale pan is light, which means that we can use a mass of 0. So when something is light, we're going to say that the mass of that object is 0. So we're going to resolve upwards. So F, that's T minus S, and that's equal to mass times acceleration. So T subtract S is 0, and T is equal to S. Now we know that T was 10.3 newtons, we found that out in part A. So we've got S is equal to 10.3 newtons. So the force exerted on B by the scale pan is 10.3 newtons upwards. So again, we found the force that the scale pan exerts on B, and then we've said that the force that exerted on B by the scale pan must be equal and opposite. So the force that is exerted on the scale pan by B is that downwards force. So the opposite, the force exerted on B by the scale pan, must have equal magnitude but in that opposite direction.